Hi, this is Math 1350 video number 2. I'm Mark Barsamian. The topic for this video is limits. We'll start with an introduction to limits, and then we will study them from a graphical point of view. This material is from section 2.1 of our book. Let's see how that looks. Here's the cover of our book, Calculus for Business, Economics, Life Sciences, and Social Sciences, brief version by Barnett and others. The material for section 2.1 begins on page 92, I believe. Chapter 2 starts on page 91. So to accompany this video, you should be working on reading the textbook. So remember that you can get to an e-text copy of this book, so you can see this exact same thing that we're looking at on my screen by going through the MyLab Math in Blackboard. So the reading for this video's material is pages 92 through 96. So there's page 92. We can go all the way to page 96. And the exercises for this material are taken from the end of the chapter, which is, I think, page 101. Page 102. So you will be working on the exercises in the online MyLab Math system, but they correspond to exercises that are in the print copy of the book. And as I mentioned in the first video in the live meeting at the beginning of the semester, I strongly urge you to consider getting the print copy of the book, the loose leaf or hardbound or copy of the book. All right, so let's start discussing limits. So before we discuss limits, it's useful to remember or to recall the terminology and notation of functions. This material is not in section 2.1 because it's prerequisite material, but it is important for us to understand limits to first understand the background. So remember that a function can be thought of as a machine that takes as input a number from a set of numbers that's called this should say domain set. So, and produces as output a number that's in a set of numbers called the range set. And the notation is important. The symbol f denotes the name of the function. The symbol x denotes the input. And this whole symbol, f parentheses x, denotes the number that's the resulting output. So you sometimes call the function f of x, but really the function's name is f, and the symbol f of x stands for the output that results when you use an x as the input. And it's worth recalling the relationship between functions and graphs. You make a graph by having the horizontal axis for the input numbers, the vertical axis for the output numbers. If an input A causes an output, this should say f of A equals B, then the point A comma B is on the graph and vice versa. So here's a picture of a situation where an input of A causes an output of B, so the point A comma B is on the graph, and we write that f parentheses A equals B. So for instance, if we had the symbol f parentheses 2 equals 7, that would tell us that for the function f, an input of x equals 2 causes an output of y equals 7. And it would tell us that the point 2 comma 7 is on the graph of f. All right, that's review of functions, function notation, and graphs. Now we're ready to discuss limits. We'll start with the definition of limit. First of all, this symbol, we write the following. So we write LIM, underneath it we write X arrow C, next to that we write F parentheses X, next to that we write L. This is spoken in the following way. spoken, the limit as x approaches c of f of x is L. There is a less abbreviated symbol. It looks like this. So you write f of x arrow L as x arrow c. Now, how is that spoken? So it's spoken f of x approaches L as x approaches c. Now, I still haven't told you what this symbol means, and I'm not going to quite yet. First, I want to point out what the pieces that make up this symbol are. So we have an X, we have the symbol F, we have a letter C, and we have the letter L. Here's what they are. In this symbol, this limit symbol, the letter X is a variable, F is a function, and the symbols C and L denote real number constants. Now finally, I'm ready to tell you what this symbol means. It means the following. What this symbol means is as x gets closer and closer to c, but not equal to c, the values of f of x get closer and closer to L. In this video, we're going to explore limits using a graphical approach. That is, the function f is given by a formula. And specifically, we will consider examples of the following kind. Given a graph of f, give a description of the limit behavior of f. Here we go. Here's the given graph of the function f. And in the table below, you can see that we are asked for the limit behavior. In this third column of the table, we're being asked to describe the limits of f in different situations. We're asked for some other stuff as well. So let's start with the row of this table that has x equals 1. So our goal is to fill in this table. Now we're going to start by just filling in the right two most cells in this table. First of all, let's fill out this cell here, the cell on the far right. F parentheses 1 equals what? Well, notice on the graph of f, where x equals 1, there is a hole in the graph. So there's no y value at x equals 1. So that means that f parentheses 1 does not exist. So we put D and E in the table at that location. Now, how do we fill in this portion of the table? Remember what the definition of limit is. This symbol says to look on the graph of f of x at places where x is getting closer and closer to 1 but not equal to 1, and consider what's happening with the y values. So let's zoom in on this graph and let's consider an x value that's close to 1. This is an x value that's close to 1 but not equal to 1. And let's see what the corresponding y value is. Well, for that x value, the corresponding y value is way up there. You can see that the y value is close to 4. Didn't write that very well. And you can see that if I choose an x value that's even closer to 1, like this x value, let's see what the y value is for that x value. Well, the y value comes out even closer to 4. So we can summarize this in a sentence. So as x gets closer and closer to 1, but not equal to 1, the y values get closer and closer to 4. Now remember, the definition of limit actually says something very much like that. It says that as x gets closer and closer to c, but not equal to c, the values of f of x get closer and closer to L. So we have a sentence here in the definition of limit that sounds a lot like the sentence that I just wrote down. So we can abbreviate, in other words, that green sentence by writing the number 4 here. As x gets closer and closer to 1, but not equal to 1, the y values get closer and closer to 4. All right, let's do another row of the table. Let's do the row of the table for x equals 4. So on the table, on the graph, x equals 4 happens right here. And we see that there's a point on the graph at xy equals 4, 2. Okay, well, since there's a point on the graph at xy equals 4, 2, that means that in this cell of the table, we put a number 2, because when x is 4, the corresponding y value is the number 2. Now let's think about this cell of the table. What do we put in for the limit? Again, for that, we should be considering x values close to 4, but not equal to 4. So let's choose this one. So there's our x value, close to 4, but not equal to 4. Let's see what is the corresponding y value. We see that the corresponding y value is close to 1. And let's see what happens if we choose an x value that's even closer to 4. So for instance, this red x value. Let's see what happens. What's its corresponding y value? Well, notice that the x value got even closer to 4 and the y value got even closer to 1. So our summary sentence would be the following. As x gets closer and closer to 4, but not equal to 4, the y values get closer and closer to 1. Also, as we did in the previous row of the table, we abbreviate that sentence by writing the number 1 here. So as x gets closer and closer to 4, but not equal to 4, the y values get closer and closer to 1. All right, notice that the difference between the idea of the y value on the graph and the idea of the limit. The idea of the y value is what is happening on the graph at an exact x value, whereas the idea of the limit is encapsulating a trend. It's where the graph seems to be going, seems to be heading. So we can add a line to our definition of limit that conveys that idea. The line would look like this. Here's the definition of limit that we had before. I'm going to add a line to the definition to convey what we just observed. The graph appears to be heading for the location xy equals c, L. So a couple things to notice. The letter C, oops, I didn't write the limit symbol here, I should have. The letter C that appears in the bottom of the limit symbol, x arrow C, is the x-coordinate of this location. The number L that appears on the right side of the equation, the limit equation, is the y-coordinate of this location. That's one thing to notice. And the other thing to notice is that I did not say the point xy equals CL. I said the location xy equals CL. Notice that in the first example that we did, the limit as x approaches 1 of f of x was 4. So the graph was heading for the location whose coordinates are 1, 4. So we have a hole at xy equals 1 comma 4. And we're heading for that location. There is no point there. It's just a hole. Oops. And then in the second example, there's a hole at x, y equals 4 comma 1. That's where the graph seems to be heading, for that location. There is no point there, so I don't want to say it's heading for the point 4 comma 1. It's heading for the location 4 comma 1. That's what's encapsulated in this limit symbol. So the symbol f of c denotes the y value at a particular x value. In the symbol limit as x approaches c of f of x tells us about the trend in the y values as x gets closer and closer to c. So limits are about trends. Now let's do the row for x equals -1. I can see right away that when x equals -1, there's a point on the graph. So there's a point at -1 comma 1. So that means that I put a 1 in this cell. Now let's consider what happens when I use x values that are close to -1 but not equal to -1. So let's use this x value here. So here we have x close to -1. And that's this x value here. Let's see what the y value is. We see that the y value is close to 1. But what if we consider an x value that's close to -1 but on the other side of -1? So for instance, this x value. Let's see what the y value is for that x value. We see that the y value is close to 2. So if we wanted to summarize this, there is no single y value that the y values are getting closer and closer to. So let's see if we can put that in a sentence. So as x gets closer and closer to -1, but not equal to -1, there is no single y value that all the y values are getting closer and closer to. We can't say that all the y values are getting closer and closer to 1 because they aren't. Some are getting closer and closer to 2. And you might think, well, maybe we could average those. Say the y values are getting closer and closer to 1.5. But they're not. These y values are not getting closer and closer to 1.5. These are getting closer and closer to 1. So since there's no single y value that works, we have to say that the limit does not exist. So we write DNE in this cell. So there is no single xy location the graph is heading towards. But there are some trends in the graph. Notice that when x is closer and closer to -1, but to the left of -1, the y values are getting closer and closer to 1. And when x is getting closer and closer to -1, but to the right of -1, the y values are getting closer and closer to 2. So in other words, on the left side of x equals -1, the graph appears to be heading for the location -1 comma 1. The graph seems to be heading for that location. But to the right of x equals -1, the graph appears to be heading for this location, -1 comma 2. So those are the trends that we can observe in the graph. So it would be useful to have some terminology and notation for these trends. That's the idea of what are called one-sided limits. So here are the definitions of one-sided limits. First of all, I'll write the symbol and definition for limit from the left. First, the symbol. So this symbol has an X arrow C with a superscript minus sign. This is spoken the limit as x approaches C from the left of f of x is L. What does it mean? Well, it means what I just said in words a little bit ago, but here I'll write it out. As x gets closer and closer to c, but less than c, the y values get closer and closer to L, and they may actually equal L. And the graphical significance is what we said up here. So I'll write that out. The graph appears to be heading for the location xy equals CL from the left. The definition of the limit from the right is entirely analogous, so I'll quickly write that out. So the symbol looks just the same, except you have an X arrow C with a superscript plus sign denoting from the right. This is spoken in the following way. Spoken, the limit as x approaches c from the right of f of x is L, and the meaning is entirely analogous. So the meaning is, as x gets closer and closer to c, but greater than c, the y values get closer and closer to L. So in the definition of left limit, limit from the left, we have x values getting closer and closer to c, but less than c. And the graph appears to be heading for that location from the left. In the limit from the right, x is getting closer and closer to c, but greater than c. And what's the graphical significance? The graph appears to be heading for the location c comma L from the right. So if we have this idea of left and right limits, one-sided limits, we can recast the definition of limit using those ideas. Here's how that recasting of the definition would look. First of all, we have the same symbol for limit. So we write lim x arrow c f of x equals L. And what's the meaning? Well, the meaning is that the function passes the following three-part test. Test A is that the left limit exists. The second test is that the right limit exists. And the third test is that the values of those left and right limits match. And their common value is the number L. So that could be written as a single equation. So the limit from the left of f of x is the number L, and that's also the value of the limit from the right of f of x. Okay, so now let's finish the row with x equals 1 and then fill in the empty cells in the rows that we already did. So remember the row with x equals -1, we had the y value does not exist. The y value is 1. The limit does not exist. But we had the trend that the graph appears to be heading for -1, 1 from the left, and the graph appears to be heading for -1, 2 from the right. So let's put that stuff in the table. From the left, the graph appeared to be heading for -1, 1, so we put a 1 there. From the right, the graph appeared to be heading for -1, 2. So we put the 2 there. But again, the limit does not exist. It can't because those two left and right limits don't match. But the y value did exist. The y value was the number 1. Let's go back up and double check that on the graph. the y value exists. It's the number 1 because there's a point at negative 1, 1. The limit from the left was the number 1 because the graph is heading for this location where y is 1. The limit from the right is the number 2 because the graph appears to be heading for this location, negative 1, 2, as you come in from the right. So that's our first row of a table where the left and right limits are different. Let's go back to our earlier example. On the example where x was equal to 1, if we go back up and look at that cell of the table, we found that the y value did not exist, but the limit was the number 4. So let's go back down to this new table and fill in the rest of it. So the y value did not exist, but the limit was 4. Well, if the limit was 4, that must mean the left limit is 4 and the right limit is 4. If you go back up to the graph, you see that if you want to look at the graph in terms of left and right limits, the graph is heading for the location 1, 4 from the left. The graph is also heading for the location 1, 4 from the right. Now let's fill in the table row for x equals 4. Fill in the rest of the cells. So remember, for this row of the table, the y value was 2, but the limit was the number 1. Because when we looked at the graph, there was a point on the graph at 4, 2, so the y value is definitely 2, but the graph is heading for this location, 4, 1, so the limit is the number 1. Now, the graph is heading for this location from the left. The graph is also heading for this location from the right. So I can go down to this table and fill in those cells. The limits, I want to make this green for my limits. The limit was the number 1, and so the left limit was 1 and the right limit was 1. All right, now let's do the row of the table for x equals minus 3. So for x equals minus 3, notice the following. So there is a point on the graph at minus 3, 3. That tells us that we have to put a 3 in this cell for the y value. Now let's notice the trend. Let's just write the summary. So the summary sentence would be the graph appears to be heading for that location, negative 3, 3, from both the left and the right. So that is about the trend. So that means that we would put a 3 here, a 3 here, and a 3 here. All those symbols have to do with the location, negative 3, 3. All right, let's do the row of the table where x equals 6. So let's start by considering what the y value is on the graph when x equals 6. So notice that there is no point on the graph at x equals 6. Both of these circles are open, so that means that the y value does not exist. Now, what about the trends? Notice the graph is heading for this location from the left, and the graph is heading for this location from the right. So let's write those summary sentences. So the graph is heading for the location x, y equals 6, 0 from the left. That's this location, 6, 0. And this sentence is summarized by putting a 0 here. Now, what about the trend from the right? As I just said, the graph is heading for this location, and this location is 6, 2. So our summary sentence would be, so the graph is heading for the location x, y equals 6, 2 from the right. So that summary sentence is abbreviated by putting a 2 here. x gets closer and closer to 6 from the right, the y values get closer and closer to 2, so the graph is heading for the location 6, 2. Now notice that the left and right limits don't match, so we write that the limit does not exist. All right, so your assignment, as I mentioned before, is to read the book section 2.1, pages 92 to 96, and to do the MyLab math homework assignment number 2. And that's these 4 problems. Now let's go look at those problems. Let's see. Those 4 problems are all about using the graph of a function to describe limits and function values. So those are just like the problems that we just did. All right, well, so that's the end of video 2, and I'll see you in the next video.